recording.
Okay, so it's my pleasure to present our next speaker. It's Genni Fragnelli. Genni is now at the University of Siena, but she did her PhD in Germany, in Nuremberg, no? So let's hear her talk. So thank you very much, Genni.
Thank you to the organizers for this kind invitation and to Lutz for the presentation. So in my talk, I will speak about new results on a particular beam equation. And these results are obtained in collaboration with Dimitri Mugnai from the University of Tuscia. In the last years, great attention is being given to also from a mathematical point of view to try to describe the behavior of particular materials, such as nanoparticles, for example, or hybrid materials, like the one in the picture, where we have a reinforced concrete. As we know, reinforced concrete is a concrete with iron beams into it. And it is realized that traditional methods are not satisfactory to describe the behavior of such materials. Think, for example, to a floor of a building built in reinforced concrete. From a mathematical point of view, this is described by an embedded beam. So the floor, if is of the building, is our domain. We require Dirichlet condition at the boundary. But from an engineering point of view, this is not realistic, since it is not true that the floor touches the wall. Actually, the floor is embedded into the wall. So the domain is larger than the one that we see. It is so the domain is actually formed by the domain that we see, the floor that we see, and the part of the floor that is inside the wall. So to describe this fact, we take inspiration by a work of Stilling. In 2000, Stilling introduced an approach called peridynamics. In this approach, Stilling consider a non-local operator of this form. So we have an integral on some set of this function f, which depends on the difference between 2 points, y and x, and the difference between u at y and u at x. In our case, u is the vertical displacement due to the vibration of the floor. Now, if we take as the set Rn, if we take as f this function, then the non-local operator is the fractional Laplacian. And if u is regular, the fractional Laplacian is given in this way. But the novelty of the approach of Stilling is the introduction of an extended boundary. So a region around the domain in which the function is defined and it is 0. So the boundary of omega is not the blue line, but the red part. And this is called the horizon. So we take inspiration by this extended boundary. And moreover, we do not consider only the fractional Laplacian, since the classical theory is important, so we have not to forget the classical result. For this reason, we add to this fractional Laplacian also the biharmonic Laplacian. So we have a mixed operator of this form. This mixed operator is not new in literature. Before going on, let us frame the problem in the reference bibliography. So recently, it is proved, for example, that if we consider the Laplacian plus this fractional Laplacian, this operator well described, for example, the hunting behavior of sharks. The first result for this mixed operator come back to the 1960 year. Indeed, one of the first results is due to Courage in 1964. It proves that A is a mixed operator if A satisfies this condition. Then there are a lot of other results, especially in the last 2 years, where this operator is studied from a different point of view. For example, studied the regularity, qualitative properties, existence of solution, the parabolic problems associated to this mixed operator. But here there is only a list of few papers, but there are a lot of other papers. But the starting points for our problem are 2 recent papers of Cluny, Busella, Mugnai, Proietti, Lippi, and Pucci, where they consider the following equation. So we have a mixed operator plus an external force like an elastic spring, and this equation lies in omega 0. Then they require the Dirichlet condition in the extended boundary. But here we have also a novelty, since we do not have the previous fractional Laplacian, but we have a regional fractional Laplacian. So the integral is not in omega 0, where the equation holds, but it is on omega. So we have 3 domains. Omega, which is the union of omega 0 and omega 1. So omega 0, for example, in the picture is the part contained in the red line, and it does not touch the boundary of omega. Omega 1 is the part of the domain between the red line and the blue line. So we consider the same domains, so omega 0, omega 1, and omega, but we consider this new operator, mixed operator. So here we have the biharmonic operator, the regional fractional Laplacian as before, plus this external force. A and B are strictly positive. And again, here we consider the equation in omega 0, but we consider the horizon omega 1, and u is equal to 0 on this horizon. So the first problem that we consider is a good definition for the space where we have to work. In particular, we do not consider the usual age to 0 omega 0, the usual Sobolev space, but we consider the following intersection, where here h as 0 is the completion of C infinity C with respect to the Gagliardo seminar. And then we require that U is defined on the extended boundary, and it is 0 in omega 1. On this space, we consider the following norm, which is equivalent, thanks to the assumption on the function b, to the following two norms, which are more useful for the computation. Indeed, thanks to this equivalence, we can prove a classical compactness result, which is the following one. Now, the second problem that we consider is an eigenvalue problem. So we consider this equation and always in omega 0. And we prove that the first eigenvalue is positive. It is characterized by the Rayleigh quotient. Then we prove that the sequence of eigenvalues is non-decreasing. Every eigenvalue is characterized by this quotient. Moreover, we have that the sequence of the eigenfunction is an orthogonal basis in the space, in the new space, and it is orthonormal basis in L2 of omega 0. And then we prove that the eigenvalue has have finite multiplicity in the following sense. Now, for a problem of this type, one can expect to obtain a result of this type. So lambda 1, the first eigenvalue, is simple, and the first eigenfunction is positive. In our case, positive in omega 0. However, this is not the case due to the presence of the B-harmonic operator with the Dirichlet condition in the horizon, which imply a classical Dirichlet condition in omega 0. Indeed, if we consider the classical B-harmonic operator with the Dirichlet condition in omega 0, it is proved that these results, so it is false that the first eigenvalue is simple and the first eigenfunction is positive. If, for example, omega 0 is a long ellipsis, so indeed there are some regions where the first eigenfunction is negative, and these results also if omega 0 is an annulus with a small inner pole. So the first open problem is the following. Is there a domain where we can find that the first eigenfunction is positive and the first eigenvalue is simple? We think that this is possible. Since if we consider the classical case, so the B-harmonic operator with Dirichlet condition at the boundary, then Boggio in 1905 proved that this result also if omega 0 is a ball. So we think that also in our case, there is a domain where we can find this result. Okay, so this spectral result can clearly be applied to static problem or to evolution problems. Now we consider as a first problem a simple linear elliptic case. In particular, we consider the following equation in omega 0. Always with u equal to 0 in the horizon. And we say that u is a weak solution of the problem if and only if u satisfies this equality. Due to the variational structure of the problem, we have that u is a solution if u is a critical point for the following functional. And in particular, we can prove the following result, the first result. So if lambda is different from the eigenvalues, we have that the functional has a critical point. So the problem has a unique solution, which is non-trivial if the function f is non-trivial. just an idea how to prove this theorem. So if lambda is strictly less than the first eigenvalue, we have that the functional is coercive, weakly lower semi-continuous, strictly convex. So we have the existence of a unique minimum. If lambda is strictly greater than the first eigenvalue, then we have to use the saddle theorem of Rabinowitz. This result is interesting if we substitute the linear term lambda u by a general function g, nonlinear function g, which depends on u. And g, for example, has a linear growth. If we consider a nonlinear generic problem with a general function f, which is a characteristic function such that f at 0 is 0, then we can obtain a similar results. Again, we say that U is a solution of this problem if U satisfies this equality. Again, due to the variational structure, we have that U is a solution if U is a critical point for this function, where in this case, capital F is the usual primitive of small f, which is 0 at 0. And now on the function f, we have to make the following assumption. So we require that f is subcritical, f is superlinear at infinity and superlinear at 0. And f, the last assumption, means that f satisfies a quasi-monotonicity condition. Indeed, this sigma is related to capital F and small f in this way. Just some comments on the last condition. This quasi-monotonicity condition is introduced in a paper of Mugnai Proietti-Lippi in 2019, and this condition improves the one of Mugnai Papageorgiou and the one of Jean in the Hilbert setting. For example, as f, we can consider the following function that satisfies all the previous condition and this monotonicity condition, quasi-monotonicity condition. But this function f does not satisfy the general Ambrosetti-Rabinowitz condition, which is a general condition to study a nonlinear problem. In particular, thanks to this Ambrosetti-Rabinowitz condition, we can prove that the functional associated to the problem satisfies the Palais-Bell condition, which is the following condition. So one can apply the following well-known Montagne-Pass theorem. According to which, if the function satisfies the Palais-Bell condition and we have this geometric condition, then the functional has a critical point. In our case, we know that the function that I gave you before does not satisfy this Ambrosetti-Rabinowitz condition, so we cannot apply this theorem. But thanks to the quasi-monotonicity condition, we are able to prove the ceramic condition, which is more general than the Palais-Bell condition, since here we have this term in front of the gradient. And thanks to this ceramic condition, we can apply the following generalized Montagne-Pass theorem. So here we have not the Palais-Bell condition, but the ceramic condition. And so thanks to this quasi-monotonicity condition, so we can prove that the functional associated to the problem satisfies the ceramic condition. So we can apply the previous Montan-Pass theorem. So in particular, thanks to this fact, we have the following existence result. We have that the problem admits at least one non-trivial solution. So we can apply the Montan-Pass theorem if lambda is strictly less than the first eigenvalue. If lambda is greater or equal than the first eigenvalue, we have to apply the linking theorem of probabilities. In any case, we have that the functional has a critical point, which is non-trivial. Now we consider an evolution problem. The first evolution problem that we consider is a second order peridynamical beam type problem of this type. So we have the mixed operator, a damping in the equation, which is non-degenerate since T is, we assume that T is strictly greater than 0. And here we have an external force that can depend on the time. The equation is in E times omega 0, and then we require that U is 0 on the extended boundary. And we are interested in this case to study the asymptotic stability. So we want to see if the energy associated to the problem goes to 0. So also in this case, I'd like to frame the problem in the reference bibliography. If we consider a classical non-degenerate beam equation, so with the Dirichlet condition at the boundary, the asymptotic stability is studied for example, in this paper, or also in this other paper, if we have a degenerate damping in the equation. If the equation is degenerate, then the stability is studied recently in 2 papers. In particular, here we have an equation in non-divergence form. So the equation is degenerate since we assume that A at 0 is equal to 0. We are considering as the space domain 0, 1. We have the Dirichlet condition at 0, so classical condition, and we consider damping boundary condition at the non-degeneracy point. Then we study this problem in a new space due to the presence of the degenerate function A. In particular, we introduce the following space. We define the energy in this way. So these 2 terms are due to the damping condition at 1. And we prove that the energy is non-increasing, and in particular, the energy decays exponentially to 0 according to this law. This is a recent result obtained in collaboration with Kamasta, with a PhD of mine at the University of Paris. Then these stability results can also be studied for the divergence case. In particular, we have always at the non-degeneracy point some boundary damping condition. At 0, we consider 2 different conditions according to the degeneracy of A. For example, if A is like a power with the exponent less than 1, we consider this condition. If the exponent is greater or equal than 1, but strictly less than 2, we consider this other condition. In this case, clearly the spaces are different since we consider an operator in divergence form. In this case, the energy is the following, and again, we prove that it decays exponentially according to this other case. The stability results is also proved recently if we have the same problem as before, but with a damping with a delay. in the equation, and this is a recent result obtained always in collaboration with Alessandro Camassa and Cristina Pignotti from L'Aquila. Coming back to our problem, so the natural space where we work is the following one, where the energy associated to the problem is this one. And we prove that in this case, the stability depends on the parameter alpha. In particular, we have the following result. So if the absolute value of alpha is less or equal than 1, then the energy goes to 0. To prove this theorem, we take inspiration from a technique used by Pucci-Serri in 1996 and also in a paper of Pucci-Saldi, but with classical boundary conditions. In particular, I just give you an idea of the paper of Pucci-Serri. They consider the following equation. So here we have the Laplacian with the Dirichlet condition at the boundary. They consider here a general function Q and F, where Q and F are two general functions that satisfies this condition and this other condition. And they prove that if there exists a function K which is not integrable and satisfies this condition, then the energy of the problem goes to 0. In particular, if we take K equal to 1, we have this result, this stability results. So we take inspiration by this proof. Clearly, the proof is more complicated in our case since we have the B-harmonic operator with the horizon, okay? So it's not the same. In our case, the function Q that appear in the paper of Pucci-Serri is exactly the damping, and F is the external function. So we obtain these stability results. If the absolute value of alpha is strictly greater than 1, then the problem is not stable. Indeed, we give the following definition. We say that a function is attainable for the problem if there exists a solution such that the norm of the difference in L2 goes to 0. And we prove the following theorem. Every solution, every function that belongs to the space generated by the eigenfunction is attainable for the problem. And thus it is dense in L2. And so the problem is not stable. To prove this result, we defined UK as the product of the eigenfunction times this function that depends only on t. I don't know if this happened. And we have that UK solves the problem if and only if WK solves the following ordinary differential equation. So we obtain that this norm goes to 0. And if we define U in this way, we have that U satisfies the problem due to the linearity. And this norm goes to 0. So we have our result. Now, oh, sorry, I try to, okay, I don't know what is this sign. We consider a parabolic, a peridynamical parabolic problem. Again, we have our mixed operator. We consider a nonlinear problem. We have this nonlinearity where P satisfies this condition. The space where we have to work now is the space L2, this one, and the energy in this case is the following functional. But here, for the parabolic case with the horizon, we have an instability result. in the sense that if the norm of the initial data is large enough and the energy is small enough, then we have a blow up. So to conclude some future perspective, it would be interested to study the stability for the parabolic problems for both operators, so with the Laplacian and with the B-Laplacian operator, plus the regional fractional Laplacian. And it would be also interesting to study the stability if we have a degenerate beam type operator or degenerate wave type operator, with other damping, since we study the stability for a particular damping. For example, if we have a degenerate wave equation, we have the stability is studied in the divergence case or a non-divergence case. We have these papers. Here we in the first paper of Alabocca, Nars and Logering, they consider a degenerate operator in a divergence form with a damping at the non-degeneracy point, which is linear or nonlinear. And the non-divergence case is considered in these two other papers. If the equation is non-degenerate and we have a different damping, the stability is studied in this paper. So it will be interesting, for example, to consider the stability for the fractional, for the mixed operator with the horizon, if the damping is strictly positive, non-negative, and so on, as in this paper. Another problem that we can consider is the null controllability for the parabolic problem and for the hyperbolic problem. If the control is localized in the interior, or if the control is acts on a part of the boundary. As we have seen on Monday in the talk of Lutz, global null controllability for the parabolic case means to find a control such that u at time t is 0 on the full domain. Here there is a picture when the control acts in the interior of the domain. For the wave equation, this condition is not sufficient to obtain the global null controllability, since if we have a wave from the left, a wave from the right, and if we require that u at time t is 0, these waves collapse. And if we do not require that also the velocity is 0 at the time t, then these waves start again. So we need to require that u and the velocity is 0 at the time t. So the global null controllability, as we know, is a well-known result if we consider a non-degenerate classical equation, if the coefficient is regular, not so regular. If A degenerates somewhere, is also a well-known result. For the wave equation, we know that the global null controllability for the parabolic equation can be proved for any time. For the wave equation, these are some results for the global null controllability if we have a parabolic case with a fractional operator. So we come back to the wave equation. As I told you, for the wave equation, the global null controllability cannot be proved for any time. Even if we have the simple wave equation in one dimension, we have that global null controllability also if t is greater than 2. So t has to be large enough. We have, for example, global null controllability if the control acts in the interior in this paper. In the last paper, we have also a moving control, but the equation is always non-degenerate. If the equation degenerates somewhere, we have this other paper. in this case, we have that the control acts at the boundary, so at the non-degeneracy boundary. Again, here we have a classical boundary. Okay, so classical Dirichlet condition. And in particular, I recall the paper of Labocca, Nars, and Logering, where they consider a general function A, proving that global null controllability fails if the degeneracy is strong. So think to the power with the exponent greater or equal than 2. And then there is also, I recall also this paper where the control acts in the interior of the domain. For the problem in divergence form, we have these two papers. This one is appeared last year in SICON in collaboration with the Botayamou and Mugnai, where we have a drift term. And there is also this other paper where we have a singular term. This is still subomitted. So I think that it would be interesting to extend this result to a mixed operator with the horizon. For the non-degenerate beam equation, also in this case, we have a well-known result if the equation is non-degenerate, as in this case. Or, for example, if we have a degenerate case in non-divergence form or in divergence form. Okay, but there are, since this is a new operator, there are no results about stability for the parabolic case or null controllability for the parabolic and hyperbolic case. So that's all. Thank you for the attention.
Thank you very much, Genni, for your nice talk. And now we open the microphones for questions or comments. The audio is open for everyone. So I had a question. So you had for the beam equation in non-divergence form, you put so Dirichlet and Neumann boundary conditions. What happens if you put so two derivatives equal to 0? Have you studied that case?
We are studying this case for we are studying for the stability.
Yes.
And also for the null controllability, we have some problems with some estimates.
Okay.
But, okay, but it is quite finished.
Okay. So you have really differences there, no?
Yeah.
Mhm.
Yeah. There are some boundary terms that are not 0, so this is the problem.
Okay. Okay, thank you very much. I don't know if there are more questions. Let me see. No, I don't see anyone in the chat. Other comments or questions? Well, if not, thank you again, Genni, for your nice talk.
Thank you for
Thank
your attention and invitation.
you.